So this is about embedded FRP reinforcement. So the presentation was prepared by myself and my colleagues Eva Oller and Ana Diego. This is an outline of the contents of the presentation. The objective is to present a summary of the main aspects introduced in the informative Annex R of Eurocode 2. So the presentation includes this brief summary of the contents of the paper you can find in the special issue, and all references supporting the contents can be found in the indicated paper. As in the presentation of this morning by Eva Oller about the FRP strengthening, so there are some slides to introduce a little bit the material because it's a bit different from the materials we are familiar with, and then some of other slides about specific contents of the annex. So the fiber reinforced polymer is a material formed by a matrix resin reinforced with continuous fibers. So fibers mostly provide the mechanical properties. The most used for this application are glass, carbon, aramid, and basalt. So the matrix acts as a binder of the fibers, transfers shear stresses between among fibers, provides integrity and protection of the fibers. So the most usual resins are vinyl ester, polyester, epoxy, and maybe some others. Here you can see a picture of some available products in the market for glass, aramid, carbon, or basalt. You can see that the finishing, the surface treatment is for bond and can be done by sand coating, indentations, undulations. There are several ways to do it. Some examples about the main applications of this type of reinforcement in which it may be an alternative. Probably the most important is corrosion in aggressive environments, for marine environments, salts, bridge decks, industrial facilities, or sewage treatment. Other applications taking profit from the properties are, for example, for temporary applications where cuttability is required, for example, for the soft ice in the metro tunnels. They are easy to be drilled by the tunnel boring machine. Thermal isolation to avoid thermal bridges, and due to the properties about electromagnetic transparency, if we want to avoid electromagnetic interference in medical or research facilities, electrical facilities, tramways. There are many codes or guidelines in different countries from, let's say, the 1990 or 1980. Just some examples. I would say the last and most important is that from the ACI from 2022, United States. This is only for GFRP because it's by far the most used reinforcement at that time. Canada, Italy, France, Japan. There was a FIB bulletin in 2007 for embedded reinforcement. And also this material was introduced in Model Code 2010, but now it has been extended, or it will be extended in 2020, which is still in progress. And now we will have this in Eurocode 2, in the informative Annex R. This covers bars or mesh of glass and carbon. Specifically, is said that doesn't mention the other materials. Does not cover pre-stressing. And I would say after some of the presentations, nothing is said about fire protection, and it cannot be used for seismic design. One of the most important properties to be emphasized is this behaves linearly up to failure. Okay, this is important difference from steel. The mechanical properties depend on fiber volume fraction And you may find many different products depending on the supplier and the manufacturer. So at that moment, we should be aware that we may have very different properties. The modulus of elasticity is lower than that of steel. Annex R says that must be larger than 40 gigapascals. For glass, I would say that commercial products are more or less between 45 and 60 gigapascals. And for carbon, would say 120,000, 130,000 gigapascal. The design should be based on the nominal cross-sectional area according to the annex. Some partial factors are also defined in the annex, and the background document gives indications about how they have been obtained, and even it is said that can be reduced if the supplier can guarantee that the reliability index is obtained. Another thing to emphasize is that FRP materials experience creep rupture under sustained loading. So this means it's a reduction of the strength under short-term load, so the normal test we do. So the design tensile strength is defined from the long-term strength after 100 years. And then, according to the annex, a partial factor is applied. So when not provided by the supplier, this value, this long-term value, a formula based on conservative coefficients is proposed in the annex. You can see that the coefficients take into account the temperature, sustained versus short-term load is a ratio, the aging effects. So if you apply these conservative coefficients, you see that you may obtain a very low value finally for design. Anyway, the background document gives some indications about how to obtain the long-term strength after 100, because for sure, it is more interesting to have this data than applying the equation. Probably you will have double of this or more than this value. Going to the structural analysis, what is said is just a summary of the annex. Linear analysis with redistribution and plastic analysis are not allowed for obvious reasons. No plastification, no yielding. Design by Stratton type models and stress fields is not covered. Concrete covered follows the same philosophy as for steel. So it is the same idea. The components of the minimum cover. So we must emphasize that the component due to durability is set to 0, because it is considered that we will not have problems of durability with this material, provided that we don't apply the material in an environment that can attack it, because it may happen. And in absence of more accurate information, so give some details about the minimum cover for both. Going to the ultimate limit states, bending. So the usual assumptions, no difference. So equilibrium, compatibility, material properties, you can do the calculations. Concrete crushing and FRP failure are allowed. The main differences, absence of yielding, so the calculations are a bit different. Like in that case in which you do the calculations where the steel doesn't yield, so it's the same. You can use the same ideas, and a large variety of products and properties. You may have very different values. Compression reinforcement is not considered for the resistance because tests have shown that there is a high scatter in the results. So finally, this means lack of reliability. And in the end, because it works under compression due to this low modulus of elasticity, so the contribution is quite low. Going to shear, so that part of shear is based on the same formulation as in the main text, so the critical shear crack theory, but introducing some modifications. Members without shear reinforcement, so introduce a ratio between the modulus of elasticity of the FRP and the modulus of elasticity of the steel to consider the effect of the lower stiffness of the longitudinal reinforcement. You can see these equations that were presented this morning that include this ratio. Members requiring shear reinforcement follow a form of an additive equation, so including concrete contribution for the sake of economy. This, according to the explanations in the background document, so this was adjusted after a study by the proposers, taking into account the larger deformation of the FRP, and limits for this deformation and changes in the value to calculate the contribution of the concrete at the compression, and even the angle to be chosen are given in the annex. Serviceability limit states are very important here because of the low modulus of elasticity. So we may have large cracks and deformations. So the general equations in the main text apply, provided that you are using the FRP properties. It is considered that this material has similar bond as a steel reinforcement, which may not be true always, okay? But I think, my opinion, we always have the possibility to include the bond because we have bond parameters in the equations for cracking. Simplified procedures in Annex S do not apply. Annex R includes specific table for stress and crack limits for FRP, in which it can be emphasized that crack width are limited for appearance, so the typical limit of 0.4. So this implies no need for durability reasons. And in absence of appearance and other specific conditions written in the annex, this limit may be relaxed to 0.7. Deflections. The general equations, the general method in the main text can be applied both for short and long term. So the equation we all know for short term and for the long term. So creep using the effective modulus method and curvature due to a shrinkage.
Please, 2 minutes.
The limits of span to depth ratio and simplified approach of the main text do not apply because they were calibrated for steel. Going to detail, general aspects of the main text can be applied. Something rules are given in the annex. Bending or rebending is usually not possible because these bars are thermosetting bars. So thermosetting bars must be manufactured with final required configurations. Anchorage, only 3 of the methods in the main text can be applied: straight bars, anchorage of bends, and hooks, U-bar loops. For the anchorage, the same equation, but with some modifications in the eta sigma parameter. CD, which is the parameters, if you remember after the presentation, it depends on the stress, and the CD depends on the cover and bar spacing. There are some particular rules for beams, slabs, walls, or deep beams. And finally, so the conclusions, then the FRP embedded reinforcement has been incorporated for the first time in the Eurocode, but in an informative annex. FRP reinforcement has been already applied in many projects where profit can be taken from its behavior, not generally. Main difference in design between FRP and steel reinforcement arise from the linear elastic behavior up to failure, the lower modulus of elasticity, and the long-term strength of FRP under sustained stresses. Due to the lower modulus, serviceability limit states often govern the design. Thanks.